Okay, let's get reading. Still on section 1, theory of heat. It's unit 2 though, which is refrigeration and refrigerants. Capacity goes back to the days of using ice as the source for removing heat. It takes 144 BTU of heat energy to melt 1 pound of ice at 32 degrees Fahrenheit. This figure is referred to as the latent heat of fusion and is the basis for determining the capacity rating of refrigeration equipment. The term for this capacity rating is the ton. 1 ton of refrigeration is the amount of heat required to melt 1 ton of ice in a 24-hour period. Since it takes 144 BTUs of heat to melt 1 pound of ice, it would then take 2,000 times that much heat to melt 1 ton of ice. Brackets, 2,000 pounds equals 1 ton, close brackets. 144 BTUs per pound times 2,000 pounds equals 288,000 BTUs. When the melting of 1 ton of ice is accomplished in a 24-hour period, the rate of heat transfer is 12,000 BTUs per hour, which is 288,000 divided by 24 equals 12,000. Or 200 BTUs per minute, which is 12,000 divided by 60 equals 200. When heat is transferred at a rate of 12,000 BTUs per hour or 200 BTUs per minute, we refer to this as 1 ton of refrigeration. For example, an air conditioning system that moves heat at a rate of 24,000 BTUs per hour is referred to as a 2-ton system because 24,000 BTUs per hour divided by 12,000 BTUs per hour per ton equals 2 tons. 3.4. The refrigeration process. The components of the refrigerator have to pump the heat up the temperature scale from 35 degrees Fahrenheit or 0 degrees Fahrenheit refrigeration compartments to the 75 degrees Fahrenheit room. Figure 3.4. Okay, figure 3.4. Heat that leaks into the refrigerator from any source must be removed by the refrigerator's heat pumping mechanism. The heat has to be pumped from the cool 35 degree Fahrenheit interior of the refrigerator to the warmer 70 degree Fahrenheit air in the room in which the refrigerator is located. Heat leaking into the refrigerator raises the temperature inside but does not normally raise the temperature of the food an appreciable amount. If it did, the food in the box would quickly spoil. When the temperature inside the refrigerator rises to a predetermined level, the refrigeration system comes on and pumps the heat out. The process of pumping heat out of the refrigerator could be compared to pumping water from a valley to the top of a hill. A water pump with a motor accomplishes the work. If, for instance, a gasoline engine were driving the pump, the gasoline would be burned and converted to work energy. An electric motor uses electric power as work energy. Figure 3.5. This is 3.5. Power is required to pump water uphill. The same is true for pumping heat up the temperature scale from the interior of a 35 degree Fahrenheit refrigerated box to a 70 degree Fahrenheit room. Refrigeration is the process of moving heat from an area of low temperature into an area or medium of higher temperature. We'll read that again. Refrigeration is the process of moving heat from an area of lower temperature into an area or medium of higher temperature. This takes energy that must be purchased. The following example uses residential window air conditioning system to explain the basics of refrigeration. Residential air conditioning, whether a window unit or a central system, is considered to be high-temperature refrigeration and is used for comfort cooling. The refrigeration concepts utilized in the residential air conditioner are the same as those in the household refrigerator. The air conditioner pumps the heat from inside the house to the outside of the house, just as the household refrigerator pumps heat from the refrigerator into the kitchen. In addition, just as heat leaks into the refrigerator, heat leaks into the house and must be removed. The heat is transferred outside by the air conditioning system. The cold air in the house is recirculated air. Room air at approximately 75 degrees Fahrenheit goes into the air conditioning unit, and air at approximately 55 degrees Fahrenheit comes out. This is the same air with some of its heat removed. Figure 3.6. Getting pretty technical here. This is a window air conditioning unit. Outside coil at 125 degrees Fahrenheit can give up heat to 95 degrees Fahrenheit outside air. Heat leaks into the house. Cooling coil, which is 40 degrees Fahrenheit, absorbs heat from the 75 degree Fahrenheit room air. Hot air is rejected to the outside. The outdoor coil receives most of its heat from the indoor coil through the refrigerant. Heat is transferred from the 75 degree Fahrenheit room air into the 40 degree Fahrenheit coil. Room air passing over coil drops from 75 to 55 degrees Fahrenheit. Okay. So we left off. This is the same air with some of its heat and the following statements. Figure 3.6, I don't know. Okay. Figure 3.6 and the following statements illustrate this concept and are also guidelines to some of the design data used in the air conditioning field. 1. The outside design temperature is 95 degrees Fahrenheit. 2. The inside design temperature is 75 degrees Fahrenheit. 3. The design cooling coil temperature is 40 degrees Fahrenheit. This coil transfers heat from the room air into the refrigeration system. Notice that with 75 degree Fahrenheit room temperature and a 40 degree Fahrenheit cooling coil temperature, heat will transfer from the room air into the refrigerant in the coil. 4. The heat transfer makes the air leaving the coil cooler about 55 degrees Fahrenheit. The air exits the fan at 55 degrees Fahrenheit. 5. The outside coil temperature is 125 degrees Fahrenheit. The coil transfers heat from the system to the outside air. Notice that when the outside air temperature is 95 degrees Fahrenheit and the coil temperature is 125 degrees Fahrenheit, heat will be transferred from the system to the outside air. Careful examination of figure 3.6 shows that the heat from the house is transferred into the inside coil and transferred to the outside air from the outside coil. The air conditioning system is actually pumping the heat out of the house. The system capacity must be large enough to pump the heat out of the house faster than it is leaking back in so that the occupants will not become uncomfortable. The cycle, as just described, is a repeating cycle. This means that once one full cycle has been completed, it is ready to repeat the cycle over and over again without depleting the system's refrigerant. 3.5. Temperature and pressure relationship. To understand the refrigeration process, we must go back to figure 1.15. Oh, we gotta go way back. Figure 1.15. Where is that? Okay, it's just like specific heat values for some common substances. We've got air, aluminum, gold, ice, steel, and it's in BTUs per pound per Fahrenheit. Read that again. To understand the refrigeration process, you must go back to figure 1.15, the heat/temperature graph, where ice was changed to steam. Okay, they wrote that wrong. That's not figure 1.5. Figure 1.5. Okay, well, they messed up the book, I think. Maybe, I don't know. I don't care. I'm just going to keep reading. where ice was changed to steam. Since water boils at 212 degrees Fahrenheit at 29.92 inches Hg, which is inches mercury, pressure, it is suggested that water has different boiling temperatures at different pressures. The boiling point of water can be changed and controlled by controlling the vapor pressure above the water. Understanding this concept is necessary because water is used as the heat transfer medium. The next few paragraphs are extremely important to gain a solid understanding of refrigeration. The temperature/pressure relationship correlates the vapor pressure and the boiling temperature of water and is the basis for controlling a system's temperatures. So, if we are able to control the pressures in a refrigeration or air conditioning system, we will be able to control the temperatures that the system will maintain. Okay, that's 2 pages, page 42 and 43. See you guys tomorrow.